Okay, so today we're going to do our introduction, our lab introduction. We're going to introduce a different group of reactions. We're going to introduce elimination reactions in lab. And so we're going to start our elimination reactions by doing a dehydration reaction, right? It's a dehydration reaction. We're going to start with an alcohol and we're going to end up with an alkene. And then there's a regiochemistry question, and so we're going to again use the gas chromatograph to analyze which of the potential products we get. So if we're looking at eliminations, right, if you're doing an elimination, right, you start with things that are sigma bonded together and you add a pi bond between them, right? So it could be going from a single bond to a double bond, as we've shown here. Could be going from a double bond to a triple bond. But in this case, we're going to go from a single bond to a double bond. And so in order to do that, you have two groups that are on the carbons that are involved. We've got to take those two atoms or groups off, but leave behind electrons that can fall in and become the pi electrons of the carbon-carbon double bond. Now in this case, we're going to do a set of eliminations that we can consider polar eliminations. That means we're going to be doing eliminations where we have charged groups moving around. And there are two patterns to these kinds of eliminations. There's E1, a first order pattern, and there's E2, a second order pattern. Okay, so in E1, right, we have a leaving group, right? And we know that leaving groups, right, good leaving groups have to be weakly basic, stable molecules or ions, right? That's what it takes to be a good leaving group. So we need something on here that, if it leaves, can meet those criteria: a weakly basic, stable molecule or ion. And in the E1 mechanism, in the first order mechanism, in the first step, the leaving group leaves all on its own, right? It leaves as, right? We show the unshared pair of electrons that goes with it from breaking that bond. So it leaves, right? The fact that it has that unshared pair of electrons makes it basic. And in this case, it leaves behind a carbocation. Now, we know carbocations are good Lewis acids. But what we find is that carbocations, under appropriate conditions, can also act as good Bronsted-Lowry acids. That is, in the presence of a base, they can give up a hydrogen ion. And so, right, here's our base. So our base comes in to take the hydrogen ion, leaving behind the electrons on the carbon alpha or immediately adjacent to the carbocation. It takes just the hydrogen ion, leaving behind the electrons. The electrons in the carbon-hydrogen bond fall in, and those electrons become the electrons that become the pi bond of the alkene. And so it is this first slow step that is ultimately rate determining. There's only one reactant involved in that step, and so that makes this step first order. Hence, we call this elimination first order or E1. Okay? Now, there's another way this can occur, right? And that's the E2 way, right? Where there's a second order step where two things collide with each other. And since the leaving group leaving is the important thing, in an E2 reaction, the leaving group leaves at the same time the base is colliding with the hydrogen ion and the electrons are falling in, all in one step. When a reaction occurs all in one step like that, we call it concerted. And since our molecule with the leaving group is actually colliding with the base, that makes it second order, right? So here we get an elimination second order, or E2, right? Our leaving group leaves. It's still a weakly basic molecule or ion, so I just showed the unshared pair of electrons, and the base takes the hydrogen ion, right? The electrons from the carbon-hydrogen bond on the alpha carbon become the electrons in the pi bond. So that's the general pattern for polar elimination reactions. Okay, so if we're doing elimination reactions specifically of alcohols, the polar bond is the oxygen-hydrogen bond, right? The oxygen-hydrogen bond becomes the polar bond we look at, right? But if we look at the leaving, right, if we just focus on that leaving, right, it leaves. What leaves is the hydroxide ion, right? The hydroxide ion leaves, but we know the hydroxide ion is a strong base, right? So it is not a weakly basic stable molecular ion, it is a strongly basic ion, making it a poor leaving group, making this step too slow to be useful, right? That strongly basic ion makes that step too slow to be useful in any kind of reaction, really. And so the challenge when you're doing elimination reactions with alcohols is really, how do you make the hydroxyl group a better leaving group? Well, one of the things that we can do to make it a better leaving group is put it in the presence of an acid, right? Usually a strong acid, or at least a moderately strong acid, right? In the presence of an acid, we know that the hydroxyl group can act as the base, right? And it can be protonated because the alkyl oxonium ion is a weaker acid. Weaker, it would help if I could spell. It's a weaker acid than the strong acid we started with. And so the equilibrium of this reaction lies strongly toward protonating that alcohol. That is an exothermic step. And so one of the challenges in that step is often, what do you do with the extra heat? So often that step needs to be cooled down in order to keep that from getting too hot. Once we've protonated that, now when that leaves, what's leaving is water. And water is weakly basic stable molecule. That makes it a good leaving group. So often when we're dealing with alcohols and we need something to be a leaving group, what we make the leaving group in the end is water, because water is a good leaving group. And this is going to apply, I've shown a carbocation here, so that suggests that we're doing an E1 reaction, but also this applies to E2 since the leaving group is involved in the rate limiting step, right? So we have to do this for both E1 and E2 type reactions, okay? So whenever we're doing elimination with an alcohol, the challenge is how do we take the hydroxyl group, which is a poor leaving group, and convert it into a better leaving group. One consistent choice is to put it in the presence of an acid, protonate that hydroxyl group, so the more stable, more weakly basic water acts as the leaving group. Okay, so we're going to do our reaction starting with a molecule 2-methyl cyclohexanol. Right, so here's carbon 1, where the hydroxyl group is of the cyclohexanol. There's the methyl group on carbon 2. And we're going to use phosphoric acid as our acid. Okay, we're going to use phosphoric acid. So, the phosphoric acid, right, acts as an acid, and we're going to have our alcohol hydroxyl act as a base, right? We're going to protonate that so that we get the methyl cyclohexyl, the 2-methyl cyclohexyl oxonium ion as our product. Right? So there we go. We've got our protonated product. Now we have our hydroxyl group is protonated to this oxonium ion. That's going to make it a better leaving group. So leaving group can leave as water, which is neutral and weakly basic, leaving behind a secondary carbocation. Okay? We leave behind a secondary carbocation if it's going E1. Okay? Now, right, here is our challenge, right? We've got two potential products we can deal with, because if this is where our carbocation is, we have two different carbons alpha to that, right? This carbon is next to it and would be alpha to that, and this carbon is next to it and would be alpha to that. And each of them have hydrogens on them, right? This one has 2 hydrogens, right? This one has 1 hydrogen. And so our base, in this case, the available base is the dihydrogen phosphate ion left behind from the protonation, right? The dihydrogen phosphate ion. Right? And so we have two choices. One, the dihydrogen phosphate ion can collide with this hydrogen, take that hydrogen ion away, and leave these electrons to fall in to create this pi bond. And so we could get 1-methyl cyclohexene as our product. But our other choice is that our dihydrogen phosphate ion, acting as a base, could collide with one of the hydrogens on this carbon, right, one of the two. As it takes that hydrogen ion away, it leaves behind these electrons to fall in to create this pi bond, 1, 2, 3, and we would get 3-methyl cyclohexene as a potential product, right? And so we have the potential to make two different products. And the question is, which one might we make? And so the way we can tell is they have different boiling points, right? The 3-methyl cyclohexene has a lower boiling point than the 1-methyl cyclohexene. And while those boiling points are too close together for us to separate them by simple distillation, at least using the limitations of the condensers in our lab kits, we know those condensers, even if we use the Vigoro column, only have 5 to 7 theoretical plates. That's not enough to separate molecules this close together in boiling point. So we have to go to something that is more sensitive. And what we have used before and what we will use again is we will go in and we will do gas chromatography and identify these by their retention times based on their boiling points, right? The lower boiling one should be more volatile and should move faster through the column. So we'd expect 3-methyl cyclohexene to come out before the 1-methyl cyclohexene. Okay? Now, before we go to the GC, we want to make sure we have alkenes. And so we have two ways that we're going to do a quick test for the presence of alkene in our product mixture, right? Because the methyl cyclohexanol is a clear liquid. Our products are clear liquids. How do we know whether a reaction really occurred? And remember, that's one of the things that we try to focus on in our conclusions. So we're going to do two different tests. One, we're going to do a bromine addition. This is just like the bromine addition we've been talking about in class, right? And so we're going to use bromine in carbon tetrachloride. Bromine in carbon tetrachloride will react with and add across a double bond, right? This goes on easily at room temperature, right? It is a rapid reaction at room temperature. And what we're looking for is the orange color of the bromine in carbon tet will disappear because alkyl halides are colorless. And so if we add a few drops of our alkene, right, if we add a few drops of our alkene to our bromine in carbon tet, the alkene should react, the color disappears, and you can then conclude that you have pi bonds in your organic material. Right? So we're going to do that test. We're also going to do another test. We're going to use potassium permanganate, a fairly dilute solution, that is a low concentration of potassium permanganate, just in water. So we call this a dilute neutral solution of potassium permanganate. And if you've ever seen a solution of potassium permanganate, you know that it creates a very distinct solution that is a very dark magenta. I wish I had a different color to write with. I'd love to be able to write magenta in magenta. Right? So we have a very bright, beautiful purple solution. But when potassium permanganate reacts with an alkene, right? When potassium permanganate reacts with an alkene, we get an oxidative addition, and we get a compound called a vicinal diol, right? Or sometimes these are called 1,2 diols, or sometimes they're called glycols, right? So we're going to get a vicinal diol, but these are alcohols. And the other thing we know about alcohols is that alcohols are colorless. And so if we add our organic product, a few drops of our organic product to the magenta potassium permanganate solution, if the color goes away, again, that means we can assume there were pi bonds that were created. And so that is evidence that we got an alkene as our reaction product. Now, we said we're going to do GC analysis, right? We went through GC before, just to remind ourselves, right? When we're doing GC analysis, there's a heated injection port. We're going to use a very fine micropipette syringe to inject a very small amount of material into the heated port. The moving gas carries that onto the wound column. The winding makes it longer. When it comes out into the detector, we can detect whether we have material. And it is during the course of passing through the column that, the combination of the vapor pressure of the materials, right? A higher vapor pressure that is correlates with lower boiling point, means it will spend more time in the gas phase, right? And so it will travel faster. So it's a combination of the vapor pressure of the solute and the coating of the nonpolar coating on the inside of the column, right? So here's a picture of an HPGC, similar to the one that we will use, right? Remember that we are using a wound glass capillary column, and the stationary phase is a nonpolar coating on the inside of that fine glass tubing, right? So the stationary phase is this coating on the inside, right? That's what our molecules are interacting with. And so the question is, how much time are they spending essentially dissolved in that semi-liquid coating versus how much time are they spending off in the gas phase moving with the carrier gas, right? So this is showing separation, right? We have a mixture as it goes through. Things with high affinity to the stationary phase and lower vapor pressure tend to move slower. Things with a low affinity to the stationary phase and higher vapor pressure tend to move faster through the column. And remember that our detector, right? Our detector is a flame ionization detector, right? So there is an electric current or an electric potential placed on those plates. There is a hydrogen flame, right? There's a hydrogen flame. And whenever anything is burning, it creates ions. And so as long as the flame is just hydrogen, then there is a specific current across those plates carried through the flame. But when an organic molecule comes through and adds to the ions in that flame, as it burns, then that current increases. Right? And that is monitored as the current changes. That gives us a signal, and that's when we know that something is coming off of our column. And remember, we're going to integrate, right? Our recorder integrates, and that the area under the curve based on the integration is proportional to the number of moles. Got a little excited then writing my N, right? The number of moles of material that created that. And so we can use the area to compare from one isomer to the next, since they should create similar ions in the flame. So get your lab notebook put together. We will start this on Monday afternoon. If you have any questions, please let me know.